yeah, so people from different sectors. So for our speakers, we have Mr. Blaise Duvernay from the Swiss Federal Office for the Environment to represent the policymaker. We have Mrs. Rosa Soler from ADIF, which is the Railway Infrastructure Manager in Spain, to represent the CI owner. And then for industry, we have Mr. Paul Pandrea from Keller Holding. For reactors, we have Dr. Marlo Barla from Politecnico di Torino to represent the academe. And finally, we have Dr. Katarzyna Zanovic from Nerve Sensors to represent the, sorry for that, the small and medium enterprise. Okay, just a quick note in relation to the house rule. Each speaker will present for 15 minutes, after which I could entertain one or two quick clarificatory questions, and then the other questions you can just please reserve for the panel discussion. For those who are online, you are please invited to write your questions in the chat box so that we can address them later during the panel discussion. Okay, so for our first speaker, I'll introduce him with a bit more detail. So Mr. Blaise Duvernay is a Master in Civil Engineering graduate from the Swiss Federal Institute of Technology, Lausanne. Later, he had his second master degree in earthquake engineering and risk analysis from Stanford University. He is currently the head of the Coordination Center for Earthquake Risk Mitigation of the Swiss Federal Office. And yeah, Mr. Duvernay is the Vice President of the Swiss Society for Earthquake Engineering and Structural Dynamics, as well as the head of the Working Group on Earthquakes in the Swiss Building Code Committee SIA 261 Actions on Structures. So without much further ado, Mr. Duvernay.
Okay, thank you very much for this introduction. As you have heard, my focus is earthquakes. I've been working for the past 20 years in earthquake risk mitigation in Switzerland. And one of our focal points is to reduce the vulnerability of infrastructure systems for this particular hazard. And so I've focused my talk today on the different aspects that we have thought as important in this field and what the needs are from our perspective. How we go about reducing the seismic vulnerability of infrastructure in Switzerland. We try to do this by identifying the specific weaknesses we can identify in the systems, and there we learn most of what can happen from earthquakes in foreign countries. And then we try to develop targeted measures that we implement in specific guidelines for these infrastructure types. And this is basically a need that we have, is that we have to be able to identify those specific weaknesses and then develop guidelines and implement measures. And you can see here a typical example for power distribution. One of the main problems of this system is the toppling of transformers under seismic action, because usually these transformers are simply on rollers. And what we have developed in Switzerland is anchoring systems for these transformers so that they cannot move around or topple over during seismic action. So it seems pretty rudimentary, but this is a bit kind of our strategy that we're implementing here. See what are the main weaknesses, develop technical measures, and implement them. One of the problems that we have identified also for infrastructure systems is the problematic of non-structural elements and equipments. Those are key elements to maintain the functionality of infrastructure systems, and usually they sustain a lot of damage during earthquakes You can see here an image of equipments that toppled over. And there are relatively simple measures to secure these elements, but they are difficult to implement in practice because there's a lack of awareness from owners and architects and so on. And also there's a lack of standardization of these products. And for that, the needs that we have identified is to develop standard solutions and products that are readily available for planners, like architects, for example. We need testing and accreditation facilities that are able to prove the performance of these systems. And we need information and simple instruments from owners and general planners so that they can implement those relatively simple solutions to reduce the vulnerability of these systems. It looks like something relatively trivial, but the implementation is really far from trivial in practice, because this is not the responsibility of a civil engineer to take care about that. This is mainly the responsibility of the general project manager, and is usually has a very low level of knowledge for these technical problems. So hence these needs that we have identified for standardization, testing, and relatively simple implementation solutions for the owners and architects. We have also identified the potential for lower damage systems. Here you see two examples: a building with the traditional conventional foundation system, a building on base isolation, and on the other side, a bridge with a conventional design where we try to keep the foundation elastic and have damage in the superstructure. And there's another way to go about this, is to keep the superstructure safe and have damage and permanent displacement in the foundation. And the systems on the left, those are the traditional systems. The profession knows how to design these, how to implement these. And the potential for lower damage systems such as base isolation or rocking isolation system has potential, but doesn't find a lot of application in practice. And therefore the need for testing facilities to validate this system. We also see the need for life cycle cost-benefit analysis to prove that this system actually cost less than they reduce the risk. This is important for decision-making persons. And there is also a need for standardization of these new systems. They are not new in the research field, but they are new for practical implementation. And I think there's a step that needs to be done from the principle to the standardization of these systems. And from my perspective, this is a big need that we have. And for that, we need to develop consistent performance-based design frameworks. It means that we have to develop simplified methods for the computation of the performance of these systems. In research institutions, we analyze the problem with very fancy and advanced methods, and mostly those methods are not suitable for a broad application in civil engineering firms. So we need to find ways to simplify methods so that they are applicable in practice on the side of the performance of the structure, as well as on the side of the definition of the acceptable limit states for these systems. Traditional design, you have action on one side, resistance on one side, and you just need to prove that resistance is higher than the action. This is kind of a black and white or 0 or 1 approach. But for considerations of critical infrastructures, you need more refined approaches where you have to define what is acceptable with what probability. And then you have to develop a code framework or a design framework system that is able to check these goals that are set for these infrastructures. And here again, we are far from methods that are applicable in practice, and hence this need to develop these frameworks in the research field. We also need a pragmatic, risk-oriented procedure for the screening of portfolios of infrastructure elements. A lot is already built. Some of it is pretty old. And a big challenge is to screen a large number of elements to pinpoint the high-risk ones for which you have to implement measures. And here's an example of the Swiss national highway bridges. We have about 4,000 objects in our road network. And we had the task to identify what are the bad risks in this portfolio. And of course, you cannot make a detailed analysis of every one of these 4,000 bridges. So we had to develop risk-oriented procedures to quickly focus on the bad ones. And this allowed us to identify about 250 bridges from these 4,000, which are not acceptable in their actual state and for which retrofit measures have to be implemented within the next decade or so, 20 years. So this is also a need that we have, is to develop these methods to identify where the bad risks are hidden in our networks. From a standardization perspective as well, we have a need to set minimum safety levels for individual elements in infrastructure networks. That means if you have systems that are already in place and you check them, for example, for their earthquake safety, you cannot expect that everything has to be 100% code compliant. You have to allow some flexibility for existing elements to be below code standards, because it would be simply too expensive to retrofit them to 100% of what is required for new elements. And that means that you need risk-based criteria to define what is the minimum threshold that has to be reached by these existing elements. I don't want to go into details with this technical figure, but this is something that we have codified for the earthquake safety of existing structures in Switzerland. We also need standardized cost-benefit criteria to roughly estimate what is sensible to invest in the retrofit of existing infrastructure elements. Here, this is also something we have developed for the earthquake safety of existing infrastructure system in Switzerland. We cannot expect from engineering firms the capability to do a full-blown risk analysis to be able to define what is the cost-benefit of measures of retrofitting schemes. This is far too complicated. And from a research standpoint, then there's the need to develop ideas or procedures to be able to assess the cost-benefit of measures so that it can be standardized and implemented relatively simply by the profession. One thing that we try to achieve, but in my opinion is almost impossible to reach, is the development of models for spatially distributed and interdependent infrastructure systems, so that you can, for instance, assess what is the consequence of a particular scenario on interdependent systems. This should be the only way to truly know what is going to happen if you have, for example, an earthquake that is happening somewhere. It's something that is a need, of course, but in my opinion, it's pretty far-fetched that we can reach this because of the high complexity and uncertainty in this field. But this is always something that we have on the radar. It's asked very frequently. For example, can you tell us what is the impact of a magnitude 6 earthquake in Basel on the power distribution in Europe? Well, it's pretty hard to say, but there is a need for these kinds of models, and of course, research institutions are in the forefront to develop this. A few more specific points, maybe more targeted to geotechnics, that we have identified in Switzerland. We have quite a lot of problems to define design frameworks or verification frameworks for embankments related to the problem of soil liquefaction during earthquakes. It's pretty difficult for us to assess, okay, what are the potential consequences on the embankment system? What are the effectiveness of remediation techniques, and what can we develop as guidelines with specific performance objectives? And here, I think the infrastructure of GeoLab surely has the potential to develop these kinds of solutions. On one side, to improve our models for the problematic, but also to test the effectiveness of remediation techniques for these kinds of works. In the field of preparedness, I think there's a lot of potential for early detection and reaction mechanisms. They are known, these systems, but they are seldomly implemented, and there's surely also potential for research in this field to try to promote and better show the potential and effectiveness of this system. For example, like automatic opening of doors for fire stations, automatic closing of valve for gas distribution system to so that there's not uncontrolled fires taking place, and so on and so forth. And this photo here is from a vacation in Canada this summer. They had a system for automatic shutdown of elevators in case of earthquakes. And earthquakes doesn't seem to be the main problem with these systems. And they have posters in the elevators to tell you not to jump in the elevator, because otherwise it's going to stop the elevator. And if you do that, you have a $1,000 fine. So there are benefits and also problems with this kind of systems. And also on the side of preparedness, surely the field of structural health monitoring systems has a lot of potential for rapid assessment of damage after an event, and earthquake is a paramount for a hazard that can affect all systems at one time, and where you need to know relatively rapidly what happened and what is still functional and what not. And also for long-term monitoring of deterioration of infrastructure elements. This is something, yeah, of course, that has a lot of potential and probably is pretty relevant to research that can be done also in the framework of GeoLab. Okay, so that would be short overview of my perspective. I hope this is targeted to the audience and your needs. And,
thank you very much, Blaise, for that very insightful presentation and for keeping within the time. Yeah. Any quick questions from the audience? Otherwise, I will proceed to our